In this video, we're going to look at permutations. A permutation is an ordering of distinct objects. If we select R different objects from a set of N objects and arrange them in order, this is called a permutation of N objects taken R at a time. The number of permutations of N objects taken R at a time is denoted by P parenthesis N comma R close parenthesis or subscript N capital P subscript R. Example 2. How many ways can the letters A, B, C, D, and E be arranged? Letters may not be repeated. Well, this is an example of a permutation problem. So we want to arrange the letters A, B, C, D, and E in different arrangements. So for example, A, B, C, D, E would be one arrangement, or A, B, C, E, D would be a different arrangement, and so on. A, B, E, C, D would be a different arrangement, and so on and so on and so on. And so we want to know how many different ways can these be arranged. So this is a permutation again because we are arranging these 5 objects, these 5 letters, in different orders. And so the question is, how many arrangements are possible? So since we have 5 letters and we're going to arrange all 5 of them, this is a permutation of 5 objects taken 5 at a time. So we would denote this as P 5 comma 5, or we could denote this as subscript 5 capital P subscript 5. So this is 2 ways to denote a permutation of 5 objects being taken 5 at a time. Now, how do we go about answering this question? Well, we can use the fundamental counting principle that we used before. So if we think about this, we have 5 letters that we're arranging. We're using all 5 letters. So when I select the first letter, there are 5 letters to select from. But now letters cannot be repeated. So for example, if I select A for the first letter, then A cannot be any of the other letters. A can only be the first letter, and the same for B, C, D, and E. So there's 5 letters that could be in this first position, and then after that position's decided, there's only 4 letters left for the second, and then there's only 3 letters left for the third, and only 2 letters left for the fourth, and finally there's only 1 letter left for the last letter. So this would be 5 times 4 times 3 times 2 times 1, or 5 factorial, in other words. So if we see what this is, 5 times 4 times 3 times 2 times 1, that is 120. So there are 120 different arrangements of these 5 letters if letters cannot be repeated. Take a look at example 3. How many 3-letter arrangements are possible using the letters A, B, C, D, E, F, G, and H, and letters cannot be repeated? So this time we're going to have only 3 letters in an arrangement, but we can pick from A, B, C, D, E, F, G, or H, so we have 8 different letters that we can pick from. So again, we might have A, B, C, we might have A, B, D, we might have A, B, E, and so on. We could, again, have lots of different arrangements, and our question is how many? Well, since we have 8 letters that we're choosing from, and we're going to pick 3 of those 8 letters, this is a permutation of 8 objects choosing 3 at a time. So we could denote this as P 8 comma 3, or our other notation, again, we could use a capital P with a 8 subscripted in front and a 3 subscripted in back of the P. So again, these are 2 ways that we could denote a permutation of 8 objects selecting 3 at a time. So what is this going to be? Well, again, we can use our fundamental counting principle similarly to the way that we did it in example 2. Only this time we're only selecting 3 letters. So we're going to fill each slot. And again, letters cannot be repeated. So if I use A in the first position, I can't use it in the second or third position. So again, we're picking from A, B, C, D, E, F, G, or H. So we're picking from 8 different letters. So that means in this first position, we have 8 letters that we're picking from, but then there'll only be 7 letters to pick from for the second letter, and there'll only be 6 letters to pick from for the third letter. So the answer is 8 times 7 times 6. So if I see what that is, 8 times 7 times 6, that is 336. So there are 336 different ways that we could arrange the letters A, B, C, D, E, F, G, or H into 3-letter arrangements. Now, this idea leads to a formula for computing permutations. So the formula for computing permutations, so this is again P parenthesis N comma R close parenthesis, or our second notation is P with a subscripted N in front and a subscripted R in back. So again, both of these notations represent the number of ways that we can order n objects if we're choosing R of those n objects. So again, this is a permutation of n choosing R. Anyway, the number of permutations of n objects taken R at a time is equal to n factorial divided by n minus r factorial. So for example, if we look back up here at example 2, then if we look at the number of permutations of 5 objects choosing 5 at a time, then that would, by this definition, be 5 factorial over 5 minus 5 factorial. Well, 5 factorial is 5 factorial. 5 minus 5 is 0, so down here we have 0 factorial. But if you'll remember, we defined 0 factorial as 1. So this is 5 factorial divided by 1, which is just 5 factorial, which would equal 120, as we said previously. It'll help a little more if we look at example 3. So again, in example 3, we were looking at the permutation of 8 objects choosing 3 at a time. So by our definition here, this would equal 8 factorial divided by 8 minus 3 factorial. Again, the 8 factorial, 8 is coming from here. The 8 minus 3, 3 is coming from here. So 8 and 3, that's where these numbers are coming from. So this would equal 8 factorial over 5 factorial. Now if we were to multiply this out, 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1. Well, the 5s would cancel, the 4s would cancel, the 3s, the 2s, and the 1s would cancel, leaving only 8 times 7 times 6, which we already said is 336. So again, the number of permutations, if we have 8 objects and we're choosing 3 of those 8 objects, is 336. Now, I also want to demonstrate that we can use our calculators to calculate permutations. So if you have a TI graphing calculator, you will find the permutation button in the same location where we found the factorial button earlier. So if I go to Math and the probability menu, if you look at option 2 on my calculator, it could be in a different location on your calculator, but it's option 2 on my calculator. You can see we have NPR using the subscripted notation there. Now, to do this, we first enter the value of n. So for example 2, the value of n is 5. So I choose 5, and then I go to Math, Probability, NPR, and so notice that the calculator puts that 5 as the subscript, and then I fill in the 5 for R. And so that gives me 120, which is the result we obtained. If you don't have a permutation option on your calculator, then you'll have to multiply it out. Likewise, example 3, we have the permutation of 8, choose 3. So I'm going to type in 8, math, probability, number 2, and then type in the 3. And that is 336, which is the result we obtained when we did it by hand. Example 4. A committee consists of 10 members. How many ways can offices of chairperson, vice chairperson, and secretary be filled? So we have 10 members on a committee, and we're going to select 3 offices. We're going to have a chairperson, we're going to have a vice chairperson, and we're going to have a secretary. And so the question is, how many different ways can those offices be filled? So this is a permutation problem. We are selecting 3 members of the committee to fill the offices of chairperson, vice chairperson, and secretary, and we have 10 members that we're picking from. Well, no person can hold 2 offices, and it matters if you are the first individual selected or the second individual selected or the third selected, so no one person can hold more than 1 office, so there can't be repetition. So anyway, we have 10 members and we're selecting 3 of them. So this would be a permutation of 10 objects, choosing 3 of the objects. So we have P of 10, 3, or if you prefer, that is 10P3 using the subscripted form of the notation. So from our formula, this would be 10 factorial divided by 10 minus 3 factorial. Now 10 minus 3 is 7, so this is 10 factorial divided by 7 factorial. Now 10 factorial means 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which I'm going to just write as 7 factorial. And 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. I'm just going to leave that written 7 factorial. So this 7 times 6 times 5 times 4 times 3 times 2 times 1 in the denominator is going to cancel with this 7 times 6 times 5 times 4 times 3 times 2 times 1 in the numerator. So that's all going to cancel out. And here I'm just being a little bit lazy. Instead of writing those all out, I recognize that this 7 factorial and this 7 factorial is just the same thing, and so it's all going to divide out. So I'm left with 10 times 9 times 8. So if we do 10 times 9 times 8, that is 720. So there are 720 different ways that we could fill the offices of chairperson, vice chairperson, and secretary if we're picking 3 people out of the 10 members of the committee. Now, once I figured out that this was a permutation problem, I could also have just typed this directly into my calculator. So I could have said 10 math probability, choose the permutation option, and type in the 3, and so that gives me 720. So once I figured out this is a permutation problem, I could have gone directly to my calculator and let the calculator determine that. Again, if you don't have that option on your calculator, then you'll have to do this out this way. So this is the idea of a permutation, and so we'll continue with example 5 and talk about combinations on the next video.